All right, chemists, let's get started. As a reminder, we have that review session tonight, so feel free to join me here in McPherson 1000 at 8 p.m. or join me via Zoom. Yes, I'm recording it. It will show up on that page, or you can look at my YouTube channel. This review session is open to all Chem 1210 students, so let your friends in other sections know. So let's continue on with chapter 3. I think we'll probably finish today. We were talking about empirical formula calculations and the idea that we can take percent composition and turn that into the simplest ratio of atoms in a chemical formula, or our empirical formula. So we can use percent composition data to do that, but the problem is that there's really no instrument in lab that can just spit out percent compositions at us. What's more likely is that chemists way back when technology wasn't that sophisticated, is that they burned things, right? Burned unknown samples. They weighed the CO2 that came off, they weighed the water that came off, and from that information, they could figure out, okay, how many moles of carbon was originally in the sample, how many moles of hydrogen were originally in the sample. And then they had to do something special about oxygen, if there was oxygen in the sample. So our strategy looks like this. This looks kind of confusing, but the idea here is that steps 4 and 5 are exactly like we did before. We just have to treat how we get the moles of the different elements a little bit differently. So the first example we did here on the next slide only contains carbon and hydrogen. So this kind of question is a little bit easier than if it contains oxygen. If it does, we have to include step 3, which we'll do an example here in a little bit. Here's another way to show how to do it. And so what I mentioned before, only do these steps if it's just carbon and hydrogen. You have to do all of them if it's carbon, hydrogen, and oxygen. So we left off with this question where I say, okay, we are, chemists back in the old days. We burned this sample. We want to figure out what the empirical formula is. We weighed how much CO2 and water came off of this unknown based upon, after completely combusting it. And so we have those masses of CO2 and water here. So the idea here is to get the moles, just like before, just like when we did empirical formulas before, to get moles of carbon, we have to convert the mass of CO2 using the molar mass of CO2. And then from there we see, okay, there's 1 carbon atom per CO2 molecule, so then it's a 1-to-1 ratio. Then we do the same exact thing with water, just using the molar mass of water. So that's why we divide by 18 grams per mole instead of 44 from CO2. And then something interesting here is we need to get to moles of hydrogen atoms. And so we have to use a 1-to-2 ratio because there are 2 hydrogen atoms per 1 water molecule, and that's denoted by the chemical formula that you see here. And so this process looks a little bit similar to our empirical formula work before. Really the only difference is that we have to just do something a little bit special using the molar masses of CO2 and water respectively here. So when you do that math right here, you get that this sample originally had 1.536 moles of carbon and 3.075 moles of hydrogen. So is this my empirical formula? Carbon 1.5 and hydrogen 3 of them? No, it's not. So now at this point, because we have mole amounts, we can figure out our mole ratio by just inspecting, which mole value is the smaller amount. So I take a look, okay, 1.5 moles, that's the smallest amount. So I'm going to divide both those numbers by 1.536. And what this does is just ensures that one of the numbers is a whole number integer, 1, because a number divided by itself is always 1. So what we see here is that for 1 mole of carbon, there is 2 moles of hydrogen. So is this my empirical formula? Yes, it is. So it's just like before. So basically those last 2 steps we did there is just like before. So in this example, our empirical formula is CH2. All right. So we just did something a little bit different here within dimensional analysis to get to moles of carbon and moles of hydrogen respectively. Same kind of idea as before. So if we look at the whole scheme of what we did here, if you look at the strategy, we did not do this last step. We basically stopped right here and calculated the empirical formula. All right, so that is our empirical formula. Let's say this question didn't ask for empirical formula. Maybe they gave you a little bit more information and said, hey, the molar mass of the full molecule is about 56 grams per mole. What is the molecular formula? So remember, an empirical formula is the simplest number of atoms in your chemical formula. So the idea here is that that empirical formula may not specifically represent the structure of the actual molecule. It's the simplest ratio. So using the information before that we got, the empirical formula, and this new molecular formula, we can figure out, okay, what is that multiplier we need to get back up to the full molecular formula? So the idea here is you just estimate the weight of the empirical formula. So to me, I know that one carbon off of the periodic table is about 12 AMU or 12 grams per mole, but then there's 2 hydrogens. So that's 2 times 1 AMU. Again, I'm just estimating. There should be more decimal places, but this is just an estimate. So I know that this empirical formula weighs about 14 grams per mole. So CH2 weighs about 14 grams per mole. And so using the information given, I can see, oh, but the full molecule weighs 56. So this allows me to get my multiplier that I need to scale up my, empirical formula. So does anyone know what the multiplier is? 4. Yes, it's 4. You know, it's not like we're just guessing here. I think what you can do to get the multiplier, if you do 56 divided by 14, you see that it's 4. All right, so whatever multiplier you use for to scale up your molar mass, you do the same thing to your formula. So our molecular formula here is C4H8, right? So there are 4 carbon atoms and 8 hydrogen atoms in your structure. Right, so that tells us a little bit more about the identity of our substance. But what you see here is I have some examples of real life molecules that all have this exact same chemical formula, molecular formula. All of these are actually C4H8, all of them, but they have way, way, way different structures. So they all have the same composition, but they all have different structures. So even though chemists were able to get the full molecular formula, they still didn't know all the details about the structure yet, but we still have some information about molecular formula there. All right, so we see this step. This step is just like what we did before when we were comparing empirical and molecular. All right, so combustion analysis is just a different way to get that empirical formula. I will say it is the harder way, all right, because we're working with not just percent compositions, but we're actually working with like CO2 and water here. All right, so here's the last combustion analysis. This is the hardest question, all right, and I will say, I can basically guarantee that there will be some type of combustion analysis question on the midterm. There always is. If you look at all the practice midterms, there's always one combustion analysis question. These are the most time-consuming questions. So if you can't get this question in a reasonable amount of time, my suggestion for you on the exam is to skip it, because it is time-consuming. But if you know how to do it and you can crank it out in 3 minutes, then do it. Because once you realize, once we go through this question, you'll see, oh, combustion analysis questions, they're always done the exact same way. Every single time, they're always worded the exact same way. So once you learn how to do it, you can crank it out. But if you don't, and you don't feel like you can confidently do this type of question, within the time constraints, I don't want you to spend 20 minutes on this question, maybe get it right, and then not have time for the rest of the exam. I'm giving you all permission to skip this question if you get to it. But if you can crank it out, then do it. So that's my forewarning. There's a lot of things here, all right? So this is a combustion analysis question again, but the difference is that this compound contains carbon, hydrogen, and oxygen, we're going to get carbon and hydrogen the exact same way like we did the previous one, where we assume, okay, all of that carbon went to CO2. So this is how we get moles of carbon. Our moles of hydrogen in our sample went to water. So we're going to do the exact same thing and convert to moles of hydrogen that way. We have to do something special for oxygen. So I'm just hold on a second there. So let's do CO2 first. We need to convert grams of CO2 to grams of carbon. So I'm going to divide by that molar mass here. Did I give you molar masses? Yes. All right. So 44 grams is 1 mole of CO2. But I don't want moles of CO2. I want moles of carbon atoms instead. So it's 1 mole of CO2 is 1 mole of carbon. I don't like to skip this step, even though it's a 1-to-1 ratio, and you may be laughing at me. It's because in water, in H2O, it's not a 1-to-1 ratio. All right, and that's where a lot of folks will screw up. All right, so that will give me moles of carbon. Now let's do moles of hydrogen. So 18.02 grams of water is 1 mole of water. And now I want to get to moles of hydrogen. So 1 mole of water on the bottom to cancel that unit out. What number goes up top? 2 moles of hydrogen. All right. So I started this question the exact same because I need to get moles of carbon, moles of hydrogen for my next step. So I'm just going to quickly put that into my calculator here. And I see that this sample originally had 0.87 moles of carbon and 2.61 moles of hydrogen. All right. So if this only contained carbon and hydrogen, we could then go figure out our empirical formula. But the problem is we need to get moles of oxygen too. We don't know if oxygen is the, smallest mole amount that we would have to divide all the mole amounts by. So we have to do something special to get moles of oxygen here. So basically the steps that I've shown right now, I've gotten us to this point in our strategy. So I like to stop at this point because I need these numbers again. So what I'm going to do is I'm going to convert these mole amounts to mass amounts, because the piece of information we really didn't use yet in this question is grams of our sample. Because if I know how much of my sample is carbon, and if I know how much of my sample is hydrogen, wouldn't the rest of the sample be oxygen if our compound is only CHO? If I know how much carbon I have, if I know how much hydrogen I have, the rest of it has to be oxygen. So that's the trick, all right? So this is what I do. I always like to stop gap at the mole amounts. And then what I'm going to do is quickly do a quick calculation to just figure out, okay, how much does that carbon weigh? So how do I turn a mole amount of carbon to a mass amount of carbon? How do I do that? Yes, multiply it by the atomic weight or the molar mass of what? Of CO2? No, of carbon, because it's carbon. We have moles of carbon. So I'm going to do 1 mole of carbon on the bottom is 12.01 grams up top. And then I do the same thing for hydrogen as well. 1 mole of hydrogen is 1.008 grams of hydrogen. All right, and so those are mass amounts. So 0.87 moles of carbon is 10.44 grams of carbon. All right, and then the gram amount of hydrogen is 2.631 grams of hydrogen. So I'll just highlight these gram amounts right here. And let's compare that to how much sample we started with. We started with 20 grams. About 10.5 of it is carbon. About 2.5 of it is hydrogen. The rest of it has to be oxygen. Do you see that? You see that? All right, that's how we get moles of oxygen, is to basically figure out, okay, how much left in the sample is oxygen. All right, so if we add those two amounts together, that's 13.07 grams of carbon and hydrogen. So that means the mass of oxygen is equal to 20 grams, because that's what was given, 20 grams, minus that number, minus that 13 number. All right, so that means our sample is 6.93 grams of oxygen. Are we done? No, we're not, but do you see where we're going next? Do you see where we're going next? We have a gram amount of oxygen. Yay! How can we get to a mole amount of oxygen? Molar mass of oxygen. And then once we have that mole amount of oxygen, we have mole ratios of every single element there. And then it's empirical formula time. So take this number, 6.93 grams of oxygen, and we do the same thing as that we did before. All right, it's grams of oxygen, so all we need to do is use the molar mass of oxygen. So 16 grams is 1 mole of oxygen, and then that should be some number, 0.433 moles of oxygen. So I'll highlight all the important things here. Here are our mole ratio amounts, our mole amounts of our elements. At this point, it's exactly like all empirical formula things we've done before. How do we turn these numbers into an actual appropriate ratio? You find the smallest one and you divide. So in this case, the smallest one is oxygen. All right, so this one's the smallest, so I'm going to divide all of them by 4.33. So do you see why? Okay, that's the wrong number. 0.433, 0.433. So do you see why I kind of stop-gapped at this mole amount of carbon and hydrogen? I didn't go straight to grams of carbon or straight to grams of hydrogen. I did a little stopgap right here because I know I need these numbers eventually. All right, and so what we get here when we divide all those numbers by the smallest, so 0.433, 1 mole of oxygen. How many hydrogens? 6 moles of hydrogen. So we get nice even numbers. And then finally, this is 2 moles of carbon. All right, and so there is our empirical formula. Okay, let me zoom out a little bit. C2H6O, one of them. All right, so that is our empirical formula. That one is the hardest. It is the hardest, and the trick is to get mass of oxygen or to get the moles of oxygen, we are utilizing the fact that, oh, I know how much carbon and hydrogen are there. I'm assuming the rest of the sample is oxygen. So that means for this type of question, I have to give you how much sample you start with. All right, so some folks, when approaching questions like this, these empirical formula questions with combustion analysis, some folks will try to balance this equation. All right, they'll try to balance this because the idea is all this carbon goes to CO2. All of the hydrogen goes to water. The problem with oxygen is that, see how there's 2 sources of oxygen? There's oxygen in your sample and in O2 in the air that's also burning there. So some folks, they'll try to figure out, okay, how much oxygen is in CO2 and water and try to back calculate to the empirical, but that doesn't work. Do it my way. Do it my way. You have to do the subtraction and figure out how much of your sample is left. All right, so these combustion analysis questions, really utilize the idea of doing dimensional analysis using molar mass and understanding the conservation of atoms here within combustion analysis or within combustion. All right, any questions? All right, so I teach it this way where I show empirical formula from percent composition and then again with combustion analysis because I want you to recognize it's basically the same question. If you know one of them, it's very likely that you know how to do both of them, right? Because they kind of fall under the same idea of finding that simplest mole ratio. And that both of these, combustion analysis and empirical formula calculation, percent composition calculations can only get you your empirical. You need your complete molar mass of your molecule to get molar mass or your molecular formula information, all right? So there we go. I would say this is the hardest, most time-consuming question on the exam. And I give you permission to skip it if you can't get it. But if you feel confident that you can do this on the exam, crank it out. All right, because it's literally the exact same steps every single time. If you look at my overview sheets, I have like 80 examples on how to do, or like different questions on how to do them. Recognize there's kind of two pathways. If it's just carbon and hydrogen that you're burning, real simple calculation. It's just, gram amounts to mole amounts, empirical formula. But if oxygen's involved, then you have to do this mess down here. But still, if you know the process, then you're good. All right, so that is the second to last section of chapter 3. I do plan on finishing this chapter. So now really is to the meat and potatoes of chemistry, and that's stoichiometry. So we kind of touched on stoichiometry a little bit with combustion analysis and the idea we're converting some atoms in one substance to atoms in another substance. And that's basically the idea of reaction stoichiometry. Once we have a balanced chemical reaction, we can use these coefficients that we use to balance, to relate amounts of moles or number of particles in a chemical reaction. I need 2 hydrogen gas molecules to react with 1 oxygen gas molecule to make 2 water molecules. So these numbers have meaning. So when working with stoichiometry, the important thing is that we always need to be working in moles of substances. When we're working in moles, we can use these coefficients. I like to call it the unit of moles is basically our ticket to ride the bus, which is the balanced chemical equation. You need to be in the unit of moles. Again, 2 moles of hydrogen will combine with 1 mole of oxygen, which will produce 2 moles of H2O. It's not gram amounts, it's mole amounts. So basically, my steps for solving stoichiometry questions is first, you need to start with the balanced chemical equation. Either you're given it or you need to come up with it yourself. Look at the pieces of information given in the question and convert to moles of that substance that's given. Because once you're in the unit of moles, you have your bus ticket to get on the balanced chemical equation, and you can go anywhere you want. So again, remember I like to use equalities like, this equals that, which equals that. When looking at these coefficients, we can also build an equality that can relate different amounts of things that we can use in dimensional analysis. So if you look at the coefficients here, what this means is that for every 2 moles of hydrogen gas that reacts, 1 mole of oxygen reacts. Where did that 1 come from? Where'd the 1 come from? Did I just make it up? No, it's part of the balanced chemical equation, which also equals, depending on where we want to go, gives us 2 moles of water. And so note that these numbers relate to the coefficients. And again, we need to be in the unit of moles. So once we're in moles of a given substance, use the appropriate mole ratio to get wherever you want to go, and then convert that mole amount of the new substance to whatever thing the question asks. All right, so let's just do some example problems. All right. So here's another balanced chemical equation. Here, I'm asking you how many moles of hydrogen would be formed by the complete reaction of 8 moles of potassium, K. So what I like to do is think, okay, we are given potassium. We're given some amount of potassium. All right, and we want to know how many moles of hydrogen are produced. So basically, we are starting here as a reactant on this balanced chemical equation, and we want to take the bus and go this way, all right? And so what's implied here, what's the coefficient in front of this hydrogen? 1, yeah, since there's nothing there, there's an implied 1 there. All right, and so the idea here, is, once we're in the unit of moles, we can use these 2 coefficients to make a equality. 2 moles of potassium equals 1 mole of hydrogen gas. Those numbers come from the coefficients. That will help us build the equality that we need to get where we want to go. So I like to start with the value that's given. 8 moles of potassium is what we start with. So look at the equality that I just got from our balanced chemical equation. 2 moles of potassium equals 1 mole of hydrogen. And then now look at the units. Will that 2, the 2 moles of potassium, is that going to go on the top or the bottom? Bottom. It's going to go on the bottom because I want moles of potassium to cancel. So note here I'm canceling the mole amount, but I'm also canceling the substance. You see how I'm canceling moles of potassium. Okay, so you want to make sure that you're canceling out the correct thing. So 2 moles of potassium, and then 1 mole of hydrogen goes up top. I really urge you not to skip this step of building the equality from the balanced chemical formula. Do it a couple times. Okay, humor me the first couple of times, because once you do it like a number of times, then you'll realize, oh, you don't have to do it anymore, because you'll understand how these fractions, when you do dimensional analysis, play out. All right, and so this one's pretty straightforward, and I think we're done. So we see that in order, when 8 moles of potassium fully react, we make 4 moles of hydrogen gas, and that's because of the coefficients that are here, that you need twice as much potassium to only make 1 mole of hydrogen gas. All right, and I always like to write the equality so I can clearly see how the fraction shows up. So let's do a harder one, because I can't look at, you know, a sample of hydrogen or potassium or water and be like, yeah, that's 2 moles. I don't know how much a mole amount of water is. But I can think about gram amounts of substances. So that's kind of more commonly measured as gram amounts. All right, so here is the same type of question. It's just I give you different starting values here. I'm asking you, okay, what mass of hydrogen would be formed in the complete reaction of potassium, or sorry, 15 grams of potassium in excess water. So it's the same idea here. We're given potassium. We're given some amount of potassium, all right, and we want to get to hydrogen. But the problem is I give it to you in grams. In order to use the balanced chemical equation, the 1-to-2 ratio, we have to be in the unit of moles. So we just need to massage the data a little bit to get it into moles before we can do the 1-to-2 ratio. So here's the strategy. We already did this. We already did the moles to potassium, moles of hydrogen thing. We already did that. That's just straight up stoichiometry. When you do coefficients, when you use the balanced chemical equation, technically that is called stoichiometry. What differs is what's kind of happening at the beginning and end. We are given a gram amount of potassium. We need to get to a mole amount of potassium. So here we use the molar mass of potassium. Once we have moles of potassium, we use stoichiometry. Okay, your 2-to-1 ratio, that 2 moles of potassium equals 1 mole of hydrogen based upon the balanced chemical equation. We do stoichiometry, we change that potassium to hydrogen, but the question asks grams of hydrogen. So we need to use molar mass again. But do we use molar mass of potassium here? No, we use molar mass of hydrogen, the mole amount that we actually have. So that's the strategy, right? You will do this a billion times, okay, in the course of even this course and 1220, where you will do, grams of a substance, moles to grams. You will do this a billion times, where you have to convert a gram amount to mole amount using molar mass. You'll do stoichiometry, and then you'll convert that mole amount to a gram amount of something else. This is going to happen a lot. So do be familiar with this strategy, going to grams, to moles, to grams, right? And you just use the respective molar masses there. So let's actually do this question. So we start with what's given, 15 grams of potassium. All right, so I want to use molar mass, so I give that to you here. So written as an equality, 39.098 grams of potassium equals 1 mole of potassium. So does that 39 number go on the top or the bottom? The bottom. So 39.098 grams of potassium is 1 mole of potassium. So we are right here. We're right here. We're in moles of potassium. We want to get to moles of hydrogen because that's what the question asks. So this is where we do stoichiometry. We use the same ratio we did before. So 2 moles of K on the bottom, 1 mole of H2 on the top. If you're really clever, you see how those units very nicely cancel. It's not just the mole amounts, but it's the substance as well as canceling. So right now we are in the unit of mole of hydrogen gas. And so I give you that molar mass right here. So 2.016 grams of hydrogen equals 1 mole of hydrogen. Okay, so the 2.016 gram amount goes where? On the top or the bottom? On the top this time, because I want the 1 mole on the bottom. Yeah, on the bottom. 1 mole of hydrogen is 2.016 grams of hydrogen. And we're done. So basically, if you compare the last slide, basically all we did was add these 2 molar mass steps. That's it. All right, in order to show gram amounts of these substances, because that's the most likely form you'll measure in lab. We can't really measure mole amounts, but you can measure gram amounts. All right, and so I think the answer is something like 0.387 grams of hydrogen is produced. All right, so the big idea, we have stoichiometry in the middle and the appropriate molar masses on the edges to convert the appropriate substances. All right, so do a lot of practice here. Well, we'll do a lot more practice here when we do BCA tables and limiting reactants. All right, so something about interesting about this question we just did, which I kind of glossed over, is that we assumed that all of the potassium reacted to make hydrogen gas. I actually made that assumption because we have potassium, but what else is also reacting here? Water. See how water is part of the reaction too? But I didn't give you an amount of water. I just said, hey, it's an excess, meaning let's pretend there's an infinite amount of water around that you'll never run out of it. So in that case, we can correctly assume that all the potassium reacts because water is an excess. The issue is that doesn't always happen. You might do a reaction where you have 2 reactants, but something needs to run out first, and it's not obvious what's going to run out first. So we need to test it. We need to test to calculate, okay, which one will run out first. A lot of the time we can use our intuition. So let me show you some examples here in the idea of limiting reactants. If we have 2 things that are reacting to make some type of product, something has to run out first. That's just how it works out. Okay, so something needs to run out first. We need to figure out what it is. All right, so the limiting reactant is the reactant that runs out first. We typically need to figure out what that is. But the idea here is once you figure out what that limiting reactant is, that reactant is the one that dictates how much product you make. That's the big idea, that your limiting reactant dictates your theoretical yield. The theoretical yield is the maximum amount of product you can make given the amounts you start with. All right, so all of that might seem really abstract, but let's use examples that you can understand. So you all make sandwiches? You know how to make a sandwich? Okay, so let's pretend we make sandwiches where we have a sandwich that's composed of 1 slice of cheese, 2 slices of bread equals 1 sad sandwich. All right, so that I have that balanced equation right there. 1 cheese, 2 bread, 1 sandwich. If I tell you you have 18 slices of cheese and 30 slices of bread, in your head, do you know what the maximum number of sandwiches you can make? Just think about it. Think about it. Okay, you have 18 slices of cheese, 30 slices of bread. How many sandwiches can you make? 15. You all did that in your head? Did you have to write anything down? You didn't have to write anything down. Okay, so in that example, 15 sandwiches, what is that? According to some of the definitions I have up here, 15 is the theoretical yield. That's the maximum amount you can make, okay? Given the starting ingredients. Because what ingredient runs out first in your scenario? Bread, you run out of bread. So if I told you with this same scenario, if I said, oh no, you can make 18 sandwiches. You have 18 slices of cheese. How would you correct me? So you would say, what? You would run out of slices of bread before you can use all the cheese. Okay, yeah, try to correct me. Yeah, so 18 sandwiches is not the correct theoretical yield because you actually run out of bread before. So do I have an example here? Yes, so a way that we can show this is using a BCA table. BCA stands for before, change, and after, and it basically is a comprehensive view of what is happening in this reaction. So I can make this question a little bit more difficult. I could say, okay, you have 18 cheese, 15 or 30 breads. How much excess reactant is left over after you make all your sandwiches? So that's a little bit more of a complex problem. So let's do a BCA table to show exactly what is going on here. You have 1 slice of cheese, 2 slices of bread gives you 1 sandwich. BCA stands for before, change, and after. So in this before line, I want to write everything that's on my kitchen table before I start. So I have 18 slices of cheese, 30 slices of bread. How many sandwiches do I have before I start? 0. Very good. And so everyone here agreed that what ingredient runs out first? What's our limiting reactant? Bread. So if bread is our limiting reactant, that is what gets completely consumed. So what I'm going to draw here, C stands for change. So do you agree with me? If all the bread is the limiting reactant, it gets consumed, I'm going to lose 30 slices of bread, and I'm going to end up with 0. Do you agree with me? If all of that gets used up. Okay. So what's interesting here is that the change line is dictated by stoichiometry. So this minus 30, if I consume 30 slices of bread, how many slices of cheese do I also consume? 15. All right, so you might be just looking at the numbers, but it also is, again, dictated by stoichiometry. If I spend 30 breads, if I look at the stoichiometry here, 2 breads is 1 cheese, so that's 15 cheeses are consumed. It's dictated by stoichiometry. All right, so we consumed 30 breads, we consumed 15 cheeses. Let's also look at sandwiches here. If we consume 30 breads, how many sandwiches do we make? Or think this way, if we consume 15 cheeses, how many sandwiches do we make? 15, but is it minus 15? It's plus 15. Yes, plus 15. Again, all of that's dictated by stoichiometry. See how this is a 1-to-1 ratio? See how this is a 2-to-1 ratio? Okay, now you just add everything up. So 18 minus 15 is 3. I'll do a different color. So 3. There's 0 breads because that's limiting, and then we have 15 sandwiches. So that is exactly what our kitchen table will look like. We will have 15 sandwiches and 3 slices of cheese left over. So the differences with chemical reactions is that we need to make sure that all the amounts in here are in moles for it to work. So let me just show you, let's pretend that you didn't know that bread would run out first, and I'll show you what that would look like. So let me just delete all of this real quick. So let's pretend that, you thought, oh, no, we'll consume all the cheese. We'll just see what that looks like. All right, so if we consume all the cheese, minus 18, so we have 0 cheese. But if we consume 18 cheeses, how many breads do we also need to consume? 36. And so when you do that subtraction, how many breads do you have left? -6. Is that possible? No. And so I hope what you recognize here, a BCA table can be really powerful because it's showing you comprehensively what's happening. So if you choose the wrong thing, you'll get weird numbers like negative amounts of bread, and you don't want that. All right, so that's why BCA tables are useful here. All right, so let's do another example here. All right, here we have a particulate view of a reaction. So this time it's an actual reaction. So we have nitrogen, hydrogen gas. Here you see the stoichiometry. There's an implied 1 in front of nitrogen gas, 3 in front of hydrogen. 2 in front of ammonia. So it's the same idea here. We could actually use a BCA table to figure this out, what this picture will look like at the completion of this reaction, but we don't have to. So how I approach this is I see, okay, we have a nitrogen gas we need to consume, but then how many hydrogens do we also need to consume if we do 1? So we have to also consume 3 hydrogens. So if we do that, we do 1 iteration of our chemical reaction. So if I consume these 4 things, what do I make on the other side? Ammonia. But how many ammonias? 2 of them. So I actually need 2 ammonias over here. Can I do the reaction again? With the stuff that's there? Yeah, so we can do it again. So 1 nitrogen and 3 hydrogens, and I will make another set of NH3s. So there's a total of 4 ammonias floating around there, right? What's missing? That last H2. Does that last H2 react? No, but is it still in the vessel? Yes, it is. So you can't leave it out of that picture. And actually, if you did a BCA table, you would see that in the after line, there would be 1 H2 molecule still left over. So yeah, in this vessel, what you'll see are 4 NH3 molecules and 1 hydrogen molecule within there. So that's another way to think about it. So let's do another BCA table, just because I want to prove to you how powerful these tables are. So here's our cheese bread sandwich example again, but a different one. Let's say you partially do this reaction, and at the end, you have 13 sandwiches, 4 slices of bread, and 7 slices of cheese. How much of each ingredient did you start with? So this question's a little bit different. I give you different pieces of information. So here, 13 sandwiches, 4 slices of bread, 7 slices of cheese. Do I put that in the before line? No, where should those numbers go? After line, because that's after the reaction has been completed. Although we don't go to completion, that's okay. So I'm going to put 13 sandwiches, 4 breads, and 7 cheese. Okay, so now it's asking how much of each ingredient did we start with. So there's a piece of information that is kind of implied here, and that's how many sandwiches we start with. Okay, assuming that we only start with ingredients, shouldn't we start with 0 sandwiches? So if I put that 0 there, we know now the change line of 1 substance, and that is sandwiches. I know that we had to produce 13 sandwiches. And then this is what allows me to fill in the rest of the table, because the change line is always dictated by stoichiometry, by the coefficients. So I know I had to make 13 sandwiches, so I can kind of back calculate now and figure out, okay, how many slices of cheese did I consume to make 13 sandwiches? Minus 13. Then how many slices of bread did I consume to make 13 sandwiches? 26. Is it plus or minus 26? Minus. And now do you see how we can fill in the rest of the table? It's like Sudoku. I think it's fun. All right, so we see, what did we start with? We started with 20 cheeses and 30 breads. Cool? Yeah. The what? In order to make, so the question is, how did I get minus 13? If I want to make 13 sandwiches, how many slices of cheese do I need? See how all of this line is dictated by the coefficients here? It's a 1 to 2 to 1 ratio. See how 13 to 26 to 13, it all fits the ratio, the coefficients. Okay, so there's a BCA table. All right, so let's do a more, let's throw away sandwiches. Okay, now we're actually going to do real stoichiometry with a chemical reaction. So here I'm telling you 60 grams of aluminum are reacting with 96 grams of oxygen to produce aluminum oxide. We want to calculate the theoretical yield of aluminum oxide in grams. So we want to figure out how much product we make. And so remember, the theoretical yield is dictated by the limiting reactant. The problem is I give you gram amounts of two things. Can you just look at that and know what the limiting reactant is? No. I mean, you might look at that and be like, oh, there's less aluminum. Maybe that's the limiting reactant, but you can't do that. You can't do that because it's all dictated by mole amounts. So the strategy here is just assume all of the aluminum reacts to make aluminum oxide, figure out how much that is, and you do the same thing for the other reactant. Figure out, okay, the 96 grams of oxygen, all of that reacts, how much product do you make? And what you're gonna do is just compare those numbers, and you'll pick the one that's the smaller amount. So literally all you need to do is just 2 stoichiometry setups, and then you just pick the smaller one. So the idea is, okay, start with that aluminum, go to product. Start with all the oxygen, go to product. Literally, you just need 2 lines and you will compare those values. So this is just like that potassium example we had, where we have a gram amount, mole amount, gram amount. And we do that over and over and over again. So let's start with the 60 grams of aluminum. All right, so I want to go to the product here, aluminum oxide, so I'm going to convert that to moles. So 26.98 grams of aluminum is 1 mole of aluminum. All right, how do I get to moles of aluminum oxide? Stoichiometry, so the coefficients. Is it a 1-to-1 ratio? No, it is a 4-to-2. So that 4 is going to go on the top or the bottom? Bottom, yeah. So 4 moles of aluminum, because that's where the 4 is in the balanced chemical equation, and then 2 moles of the aluminum oxide, Al2O3, and then lastly, just use the molar mass of the product. So 1 mole of aluminum oxide is 101.96 grams. So I'm just going to leave that equal sign there. I'm not going to calculate it just yet because I want to set up the next one. We have to do the exact same setup, figure out how much, if all of that oxygen gas reacts, how much product do we make? So it's the same exact deal, just use the correct stoichiometry and the correct molar masses here. So let's start with 96.0 grams of oxygen. Use the molar mass of oxygen gas, so 32 grams of oxygen is 1 mole of oxygen gas, okay? And then we want to get to moles of our product, so use the correct ratio here, or the correct stoichiometry. It's a 3-to-2 ratio, so 3 moles of oxygen gas go on the bottom, 2 moles of my product go up top. And now it's the exact same as the previous setup. We're already in the unit of moles of product, so just multiply by its molar mass, which is given. So moles of my product is 101.96 grams. All right, so I like to do the 2 setups and only pick up my calculator once because I'm lazy. And so what we get is that if all of that aluminum reacts, we get 113 grams of product. If all of the oxygen reacts, we get 204 grams of product. So based upon this information, what reactant is our limiting reactant? Aluminum. So how much aluminum oxide do we make? The 113, the smaller number, yes. So we actually make 113 grams of aluminum oxide. This is our theoretical yield. Does that 204 number mean anything to us? No, it doesn't. It doesn't mean anything to us. We assumed that all of the oxygen, if that reacted, that's how much product we would make. But in this case, will all the oxygen react? No, it won't. So that number really is meaningless to us here. But what that does indicate to us is that O2 is an excess in this example, where aluminum is our limiting reactant, and then this 113 grams, that is our theoretical yield because it's dictated by our limiting reactant. All right, so basically, all of reaction stoichiometry and the idea of limiting reactants is based upon this idea. All right, sometimes we'll say something is in excess. Like if I said, okay, you do this reaction and oxygen is in excess. What that means is that you're just assuming that the amount of aluminum you start with, that is your limiting reactant. Because if something's in excess, it's not going to be completely consumed, so you don't actually have to calculate it. But in this case, I did not make it obvious which one is in excess and which one is limiting, so you just have to do both. All right, so that's reaction stoichiometry and limiting reactants. So let's do one more example here, and now that's combining the idea of percent yield, and that's based upon the fact that we are not perfect human beings, and when we're in lab, we don't do things perfectly. Even if we were building sandwiches, all right, making 13 sandwiches, you have a lot of faith in me that I can make 13 edible sandwiches perfectly. The idea here is when we're in lab, you might not get all of the product that you sought out. And so that's where we get these percentages here, where your percent yield is your actual yield. So this is like what you get in lab. This is what you actually measure after your reaction is done, all right? Over your theoretical yield. So this theoretical yield comes from your stoichiometry that we did previously. All right, and then you multiply it by 100 to get your percentage. So the example here is, okay, if you have a theoretical yield for a reaction is 3.2 grams, but you only succeeded in isolating 2.94, all right? So the maximum you could have made was 3.2 grams, but you only got less than that. So we're just going to calculate the percentage here. All right, so our percent yield in this case would be 2.94 grams over 3.20 grams times 100%. I think that gives you something like a 91.9%. Right, so that would be your percent yield here. All right, and what I want you to be cognizant of is the language that's used here. All right, what is the theoretical? Here I just gave it to you, but sometimes you have to calculate using stoichiometry what the theoretical is. And the idea here is in lab, you only got 2.9 grams. That would be your actual yield. So let's do a better question, or a more applicable question here. So let's say that we are reacting 44 grams of nitrogen with 8 grams of hydrogen to produce ammonia. So this reaction again. I tell you that this reaction only produced 37 grams of NH3. What's the percent yield? So I give you amounts of the starting materials. What's this 37 gram NH3? Is that the actual yield, or is that the theoretical yield that we'll put in this into this equation? The 37, given how it's worded in this question. It's the actual. It's how much you actually collected in lab. So that's the 37.0 gram. That's your actual. So in order to figure out what your theoretical yield is, you need to figure out, what your percent yield is, you need to figure out what your theoretical yield is. So this requires us to do another setup of stoichiometry, figure out which one is the limiting reactant. Because I give you both starting amounts of nitrogen and starting amounts of hydrogen. So I don't actually know what the theoretical yield is. I need to figure out what it is. So this setup is just like our aluminum oxide question. We need to do 2 setups and figure out which one runs out first. So I'm going to do the NH2 first. All right, so I'm going to assume all of that nitrogen gas N2 reacts, but I need that to be in a mole amount, so 28.02 grams of N2 is 1 mole of N2, and then 1 mole of N2 is 2 moles of the product, NH3, and then I want to turn that into a gram amount. So 1 mole of NH3 is 17.03 grams of NH3. So this should look very, very familiar from your aluminum oxide example we did before. Okay, we're just going to take that theoretical yield and do something with it. All right, and then we do the exact same thing with hydrogen. So 8 grams of hydrogen. On the bottom here, I'm going to put the 2.016 grams of hydrogen is 1 mole of hydrogen gas. Now I do stoichiometry, so 3 moles of hydrogen on the bottom is 2 moles of ammonia up top. Whoops, and now I need to get the mass of ammonia, so 1 mole of NH3 on the bottom, 17.03 grams up top. And so what I get for these two values is if all the nitrogen reacts, you get 53.48 grams of NH3. If all of the hydrogen reacts, 45 grams of NH3 is produced. So which number matters to us, 45 or 53? 45. So that's how much we actually produce. That is our theoretical yield. So that's the number that goes into our percent yield calculation. And you get that if you do 37 divided by that 45 number, you get a percentage like 82.1% yield. All right, so there's one more slide, so we'll finish that on Wednesday, but you have all the information you need now to do all of those practice exams, because we're essentially done with chapter 3. We will do that last slide, all right? So I hope to see you at the review tonight.